Okay. Okay, let's start from the beginning. So today is lecture 6, and we are going to study uh, the main title of the course is same like ultrafast lasers. And in this lecture, we'll dedicate our time to the gain and the cavity optics, essential things, okay, but not the pumping here. So if you see here in the first slide, it will come later, so I'll explain later. Okay, so amplification and gain. As I mentioned that we have a gain medium. The gain medium is basically what? Laser medium. So if there is a gain medium, there will be a gain as well. Okay, and the degree of amplification, how much a thing can be amplified, that we call it gain. Okay, so gain formula is here, you can see, and this one, if you integrate that formula, okay. You will also see the plot down, okay, and to the plot I will come later. First, look at the points which I have written there, and these are like I is the intensity, I naught is the initial intensity, okay, and G is a gain, and X is a distance, okay. So this I naught initial intensity at 0 point, okay, at zero distance, you can say. So what this formula is showing, you people know very well, you are learning this thing from the high school or maybe before, that it shows that exponential increase in the intensity, okay. So exponential increase in the intensity, you can see the plot down here, it's animated, okay. So there are three lines you have seen here. The blue one, when you see the colors, isn't it? The blue one is when G is 0.5 plus 0.5. The red one is decay actually, when the G is minus 0.5, and the constant when the G is equal to 0 is a constant. So you can see here, when the growth is going on, it's growing the signal. So you see that this blue color, okay. And when the constant stuff, when the gain is a constant, then you see the green. And when the gain is decaying, this is the red portion, okay. So like a normal amplifier, this laser amplifier, the gain should increase. If the gain is decaying, then it's a useless, okay. So this plot actually, it's showing very well. When the gain is equal to 0, then there is no growth. And when the gain is positive, it's growing. When the gain is negative, it's decaying, okay. And intensity increases exponentially, okay. This is exponential increase. And as the light beam is propagating through the gain medium or amplification medium or the laser medium, okay. So with the passage of time, gain is, but how this gain will be increasing? Gain will not be increased without doing anything. We have to do something to increase the gain, okay. So first thing, pumping has to be done so that the stimulated emission and population inversion. Second thing, the cavity, two mirrors on the side, or the very long gain medium, okay. In this way, the gain will be positive. In other case, gain may be negative or may be constant, 0, okay. So now if we move to the next slide, same topic, amplification and gain. Okay. As I mentioned before, the laser material, the gain medium, uh, it has a very low gain in case of lasers. Okay. And this gain, you can see, is of the order of 0.0001 per centimeter, or it can be like 0.01 per centimeter. Okay. So what is the meaning? Meaning is that when the light is traveling for 1 centimeter, the intensity increasing only about 0.01% to 1%, which is the rare case, usually 0.01%. Okay. And this is very, very low gain. Okay. So this thing we have to keep it in mind, that the gain of the laser material is very low. So it means we cannot have a laser action until we amplify a bit. And how we can amplify? We have to amplify by using the cavity mirrors, a resonator. Okay. Two possibilities here. You can see in the down as well. This is a gain medium enclosed in the cavity, and this is the gain medium without the cavity. Okay. If we, this thing is impractical. It's not practical. Whether to have a very long gain medium. Okay. Meters. Okay. So that the photons are multiplying, and again, we may expect that the gain will be increasing. Okay. And other possibility to use the mirrors. So if you use the mirror, then the to and fro movement, to and fro, to and fro, again and again, they are passing through the gain medium, so it's amplifying. Other possibility, if the gain medium is very long and the photon is starting from here and multiplying, which is not practical actually. Okay. So resonator, the cavity, is essential part. Okay. So there is an example here. If you see this green portion here, so material whose gain is 0.001 per centimeter, and we wish to achieve the amplification of thousands time. So if we calculate this thing, you can try by yourself. If the gain is 0.001 per centimeter and we wish to have a thousands time amplification, so it means that light has to travel about 69 meters in a medium. 69 meters. Definitely, which is not practical. You cannot have a 69-meter long gain medium. Where will you put it? Okay. And how to pump it? So this is impractical. So that is why if we use the two mirrors, we can have a to and fro, but again and again passing through the medium, and this thing can be compensated. Okay. So this is why this topic is today, to understand why we need the cavity resonator and what is the importance of the gain. Okay. And same thing is mentioned in this figure, whether to have very long gain medium, which is not practical, and whether to have the cavity mirrors. Okay. Same thing here, just to animate it here, like this is 1 meter, 100-meter long gain medium. Okay. So if we use the mirrors here, if we use the mirrors, so probably we can have very small length of the gain medium or the laser material, but it will be producing the same effect what this material will, the longer one will produce. But if we have the mirrors, okay, it's moving to and fro, something like this. Okay, so this is the importance of the cavity mirrors. Now move to the next slide. Gain and loss. In real life, this gain and loss is always with you in every aspect of life. In science experiment, in daily life, or whatever it is, the gain and the loss. In case of laser, the gain should overcome the losses to have an effective laser action. Okay, you can see here and here that to have effective laser action, the gain has to be greater than the losses. Okay, the gain has to be greater than losses. You cannot prevent the losses. When there is cavity, the cavity mirrors, tube, crystal, any container or something like this, there always be losses. You cannot make anything loss free. Okay, so what we can do to have enough gain, to have enough gain to have enough amplification to overcome the losses. So whenever the photons are moving to and fro in the cavity, like here, they loss and gain, loss and gain. But if there is no pump, or if we don't have a cavity, then losses will be increased and the gain will be reduced. Okay, so losses are supposed to be greater, sorry, the gain is supposed to be greater than the losses. Okay, so what you see here, here we say alpha is a loss and the gamma is a gain. Okay, this is a cavity mirror 1, this is cavity mirror 2, and the loss we say is directly proportional to this relation and the gain is directly proportional to this relation. Okay, both things are exponential. Okay, the loss and the gain. Loss decay exponentially maybe when the gain grow exponentially. When the gain decay exponentially, maybe loss grow exponentially. Both are exponential functions. Okay, and L is the length of the cavity, which is obvious. So this gain is supposed to be greater than this loss, so we can have a laser action. Okay, and I mentioned to you that losses can be many reasons. Okay, things can be absorbed in the cavity around, in the atmosphere around, photons scattered around, light can diffract. Okay, so that is the losses. This is the reason of the losses, which we cannot prevent. Even if we make very perfect system, we cannot prevent. So the opposite way to increase the gain, which is in your control somehow, through pumping, through the cavity mirrors or something like this. Okay, so gamma is a, this gamma is a gain coefficient. Okay, so gain coefficient, you can say per unit volume. Okay, so now we move to the next slide. When we study the gain and amplification, the one word comes which we call threshold. Okay. So threshold is a point. After that, you really see something is changing. Called threshold point. Okay. When you pump, it's not necessary that you get the laser action in the beginning as soon as turn on the pump. No. You can see here in this animated graph, it's here. When the pump energy reaches to 4, any arbitrary value I'm using here, then the output power of the laser abruptly increase. Okay, here. Before that, even though power is increased, or sorry, pump energy is increased, but you don't see the laser output, the output power. Okay, so there are always threshold value.
I'm sorry.
Yes.
I'm sorry. Are you sharing the screen?
Yes, all the people are.
Okay, I cannot see it.
How about other people? They can see the screen?
I can see the screen.
Yeah. So if you can see, then it means all should see. Check your system, Fatima. Okay. So what are the points here? We don't see output until the pump approaches to a threshold value. Okay. And after that, higher the pump energy, and then you get higher the output. And but it cannot be infinite. It cannot be like if it is increasing and keep increasing. It has a limitation as well. Okay. This is just to show, but it doesn't mean that it increase forever. No, it's not like this. Okay, that is a different story. Okay, move to the next slide now. Now, what happened inside the cavity? Steady state oscillations. Waves and oscillation, you people must have studied in the high school or the university or something like this. So, condition 1. There are so many waves there in the cavity, even though we think that there may be a 1 wave, 2 wave, 3, but it's not like this. It's always there. Okay, and for the steady state oscillations in the cavity, the condition number 1 for the proper amplification, the waves which are making round trip should maintain the phase conditions. Okay, you can see here it's written. Okay, so the phase difference or phase delay must be some multiple of 2 pi. Okay, so 2 pi can be a 4 pi as well, and so on, 6 pi, something like this. So it's animated down. If you see here, even though there is a phase delay or a difference of 2 pi, but still the waves are overlapping. Okay, so overlapping waves will be amplified. Okay, but if there is a phase difference is less than 2 pi, let's suppose it's pi by 2 or something like this, then these waves, if any wave has this kind of phase difference, which is not multiple of 2 pi, then that wave will be cancelled out because of the destructive interference. Okay. When you have trough to trough, crust to crust, it means the waves are interfering constructively. Okay. Like here, this waves is interfering constructively, and this one with this one. It started after 2 pi delay, but in phase with the first wave, and the third one after 4 pi, but still in phase with the second one and the first one. If the wave is generated from here somewhere, then it will be out of phase, and that wave will not be amplified. That would be cancelled out because of the destructive interference. Okay, so this animation, it helps you to understand how the waves in the cavity can be. Okay, you cannot, portray exact phenomena is going on, just to make it possible to understand. Okay, same thing is I drew with my hand here, the 2 pi. Even though delay is 2 pi, but still they are overlapping with each other. So it means they have a constructive interference and they will be amplified. Okay, move to the next slide. Second condition, this is the first condition. Okay, if the waves having a phase delay of 2 pi, multiple of 2 pi, can be 4 pi, can be 6 pi, okay, multiple of 2 pi, but not multiple of pi, and not multiple of pi by 2, something like that. Now, condition for steady state oscillation, second condition. Second condition, this equation should satisfy. 2L is equal to n lambda. There is also mu in it, but it's not necessary to write here. So the length, L is the length of the cavity, lambda is a wavelength, n are the order. Okay, so it should satisfy the 2L twice. 2L means, like here, if you see, if you go in this direction, L, if you come back in this direction, sorry, if you come back here, L again. So L plus L is equal to 2L. Okay, so now look at the points here. Inside the laser cavity, you know that the light bounces back and forth between the two mirrors. Okay, this is obvious. For the waves to have constructive interference or to construct itself after each round trip, the path length must fit an integer number of wavelengths. This point. Okay. N1 lambda is equal to 2L. N2 lambda is equal to L. N3 lambda is equal to 2 by 3L. Okay. So for the wave to construct, it hit from one mirror to another mirror. Okay. And after striking or shining or moving to and fro between the two mirrors, it reconstruct only if it follows this equation and 2 pi condition. Okay. So for the wave to reconstruct itself after each round trip, the path length must fit an integer number of wavelength. Okay? Integer number of wave 1, 2, 3, 4, whatever. So L, you know, that's the cavity length. Okay. And one round trip, it means is 2L. Okay. And this point, if you see, a wave only reproduces itself after a round trip if the path length 2L equals an integer number of wavelengths. Okay, not only one, integer number of wavelengths, 1, 2, 3, 4, 5, something like this. So condition has to be satisfied. Okay. So if you see in the yellow portion here, what is written? Only those wavelengths that satisfy the condition can form standing waves inside the cavity. Other waves are, they cannot be reconstructed. Okay. They would have a destructive interference or they destruct each other. Okay. And these allowed wavelengths, which following this formula, we call it resonant cavity modes. Cavity mode will come in detail later on, which are very important for the ultra-fast laser. Okay. So these allowed wavelengths, we call it the resonant cavity modes. Okay. So all the other than that will interfere destructively. Okay. And cancel out. We don't see. So if these conditions are following 2 pi and 2L is equal to N lambda, then you have a constructive interference and you can have an output. Other waves which will not be following these conditions, then they will be cancelling out. Okay. So these are the two conditions. And here, what you see here, that is N, standing wave modes, or this N value. N1, if there are two waves, then N2, if there are three waves, then N3. You can see here, this is 1, this is 2, this is 3. Okay, it helps you to understand. Now the same thing, but this L is very important. This L is the length of the cable. Okay, how we decide what wavelength we can have at the output? That length will decide. So we have to design the cavity with a certain parameters. If we want to achieve the wavelength, what we want to have. Okay. So rearrange this equation. It will be like L is equal to N lambda over 2. Okay. There is a refractive index here, which is, I assume, equal to 1. Okay. And if we substitute here different value of N, here we have lambda 1 2L. This is the second. Lambda 2 is equal to L. Lambda 3 is equal to 2 by 3L. And lambda 4 is equal to L by. So if these conditions are satisfied, you can see these waves will be surviving and reconstruct along with the 2 pi condition. Okay. And other than that, if there is N value is equal to 0.1 or something like this, it will not be feasible to reconstruct the waves in this way. So the integral multiple of the wavelength within twice the cavity length, follow the formula, is amplified strongly. Okay. And other wavelength will be attenuated. So whoever the waves, they're following this condition, they are amplifying strongly, and other than that, they are attenuating. Okay. So this is how in the cavity the things works. Let's move to the next slide. Now, much easier to understand for you people. This is still the steady state oscillation in the cavity. Okay. So we call it axial modes, what is written here. And the length, the cavity length, should accommodate the integer number of standing half waves S. Okay, so what do you see here? If you have N1, N2, two nodes here, N3, three nodes here, N4. Okay. This one, if there is N1, we call it fundamental, the first harmonic. If there is N2, then we call it second harmonic, F2. If there is third one, then we call it third harmonic, F3. And if there is fourth one, we call it fourth harmonic, and so on, fifth harmonic, sixth, seventh, whatever. Same thing you can see in animation here. This is the N1 case, okay, and this is N2 case. You can see here, okay. This is N3 case, and this one is N4 case. 1, 2, 3, 4. So this is how the standing waves in the cavity is produced. Okay, so this is what's going on in the cavity, and the conditions are supposed to be fulfilled. And this length L, as I mentioned, that is very important. Whenever you design, whenever you build the laser, the length of the cavity is decided according to the wavelength. Okay, along with some other things, but in a simple words, this length of the cavity. Okay, similar kind of thing, but in a different way, the cavity resonance frequencies. We have a formula here, this one. This is the refractive index. Okay, we can use better. This is the wavelength formula. This is the frequency formula. So this formula can also be converted to the frequency. Okay, these are the steps here. Okay, lambda is equal to C F frequency, and then you can substitute and you get frequency. Okay, so that is why, because this lambda formula is converted to the frequency, we call it cavity resonance frequencies. Okay. Now, these frequencies are supposed to be in the cavity, even with a certain length. Okay. But all these frequencies cannot be amplified. Okay. If you see in this wave here, this is a lambda here. Okay. And you will see the lines here as well. Here, these lines. These are the modes now. We call it resonant frequency COM. Maybe you may have a confusion. These are the frequency separations. These are the frequency separations according to this formula. Okay. But anyway, I mean, this is, it's confusing at the moment, but later on you can understand. So yeah, this, at the moment here, what I wanted to show that the wavelength formula is converted to the frequency, and we call it cavity resonance frequencies. Somebody's mic is on. Anyway, okay, so then these lines, you see, these lines are the separation, the frequency separation in the cavity. That will come later. Okay, here. Cavity resonance frequency. Okay. This is the formula. Okay, from this to this, this to this, this to this, 1 to 1. So the separation between each and every line is delta nu is equal to our C over 2L. Okay. So what we call these frequency separation lines, we call it modes. Longitudinal modes. Why it's longitudinal? Longitudinal means it is along the length of the cavity. If this is the cavity, waves are moving like this. Okay, so these modes are developing here. Okay. So if you see the first point here in the slide, it's not possible. There will be, if you calculate, there will be so many frequencies. Okay, the oscillation, laser oscillation. But it doesn't mean that the laser oscillation, the cavity will occur at all these frequencies. It's impossible. Okay, there are many frequencies inside, but not all the frequencies. Okay. So laser operates only on the few selected frequencies. You know that it depends on the length. It depends on the condition 1, condition 2. Okay. And there is another condition. That is the gain of the gain medium, laser medium. So how much gain is the gain curve of the laser medium? So that much frequencies will be amplifying and oscillating. You will see in the coming slides. So meanwhile, the red portion you can see here. So laser operates only at selected frequencies for which the gain exceeds all the cavity losses. Okay. So at some frequencies, gain cannot exceed the losses. So the spacing between any two neighboring frequencies is this one. Here. Equally spaced. It's equally spaced. Again, the cavity resonance frequency, this is just for you people to see the conversion procedure. The last frequency equation on the previous slide can be written in the wavelength and wavelength to frequency or something like this. Okay, this is just a conversion you people can see. Okay, this is a very important slide here. Very interesting slide. These we call this kind of appearance of the frequency mode, we call it longitudinal modes. Okay. This is the gain curve of the medium. Okay. Gain curve of the medium. There are so many frequencies here, but all these frequencies cannot enter in this gain. Okay. So other than whoever enter in this gain, other frequencies will not oscillate, will not amplify. So if we combine this thing and this, we get this one. So only these modes or frequency separation of frequencies can oscillate because it's under the gain of the medium, which medium we are using. Okay. So even from here, most oscillating frequencies will be here. These will be less. Go to the left side now. This is very interesting animation. It will help you to understand. Here you see, these are all the frequencies and we have a gain curve. So the sum of the frequencies are accommodating in the gain curve, the black one. Okay, and that is the point where these frequencies will be oscillating and these frequencies will be amplifying, something like. So narrow the gain, narrow number of frequencies, broader the gain, more frequencies will be in the gain curve. Okay, normal laser, the gain curve is usually narrow, but if you go to the ultra-fast laser, the gain curve is very broad. So many modes come in it, many frequency modes come, many longitudinal modes come in. Anyway, so this is the relation gain and the resonant frequency. Okay, so only those frequencies will be oscillating and will accommodate and will be amplifying if it fit in the gain curve here. Okay, and here also actually. So these rest of the frequencies will not be oscillating. It will be there in the cavity, but it will not be amplifying. It will not be contributing. It may cause a noise, but it's not coming out in any case. Okay. Same thing. You can understand more maybe. So here, all these lines, these frequencies will nothing to do with laser action. So which is occupying by the gain curve here, that is important. So that frequency, how many will be? That will be oscillating, that will be amplifying. Okay. So, okay, so this is how the laser amplify. Okay, the gain of the medium is very important. And this gain actually, it helps the certain frequencies to amplify because in the gain medium, all the things are happening. Stimulated emission and the population inversion and everything. Now move to the cavity optics. What are the cavity optics? Cavity optics, we have a cavity here. Okay, what kind of optics are used? Different configurations, different techniques. Okay, and why do we need these cavity mirrors? Okay, technical word you can see here. Like in order to create a huge flux of photons as they pass down to a lasing medium. Okay, and gain medium is very important, as I mentioned you before. So stronger the gain medium, better the output laser. Okay, the cavity mirrors required to contain photon within the cavity. You know that. But even in this case, there are scattering, absorption, etc., things are going on. Keeping energy density high for further amplification. Okay. As I mentioned, these things are mentioned, before as well. These mirrors are supposed to be very efficient, very good quality. It can be dielectric mirrors, okay, and efficient reflectors. It has to be, and one side is almost 100% polished. Other side, from where the output comes, can be a 98%, 95%. It depends on the gain of the laser, but it has to be less than the polished side. And it is called output coupler. Output coupler, from where the laser is coming out. So the condition is that the mirror is supposed to be aligned very well so that the photons are supposed to be trapped, completely trapped. So if the photons are escaping from the cavity, from the resonator, it means there are losses which affect the output power. It has to be very nicely aligned. There are some kind of lasers which we call super radiant laser. Super radiant laser. Super radiant lasers, they don't need cavity mirrors. It's good to have, but they can also work without cavity mirrors. You can see this is homemade nitrogen laser. Nitrogen laser is super radiant laser. When we made the nitrogen laser, we didn't use any kind of cavity mirrors. And the wavelength, the output wavelength of the super radiant laser is not decided by the cavity length. No, because there is no cavity. It is decided by the frequency of the energy level transition. So, first point here, these kind of lasers, super radiant lasers, they have a huge gain. And light is amplified to a certain level in a single pass even. Okay. And these lasers are not supposed to be discussed here, but anyway, a little bit I'm telling you. So these lasers operate without cavity mirrors. It has a narrow line width, very narrow spectrum. Okay. And the frequency or the output wavelength is set by the atomic transition, not by the optical cavity. So what is atomic transition from this level to this level? Okay, so E is equal to h nu. So this frequency will decide according to these energy levels difference. Okay, so this frequency can be converted to the wavelength. Carried here, the light produced has a frequency that exactly matches the natural energy difference between the two atomic states. Okay, so one of the example of these is nitrogen laser, so called molecular nitrogen laser also it is called. And neutral neon laser also exists. Molecular hydrogen laser exists, and copper vapor laser also exists. And what is also mentioned here, this is a book. Okay, I'm one of the co-author and some of my other students. This book is available on Amazon. This is entirely based on the nitrogen laser. How to build the nitrogen laser. It's some theory and some other stuff also. How it works and how it can be built. So if you like, and if you have access to probably David already has this book. David, are you there or you left?
Yes, I have the book.
Yeah, you have that book. Okay. So if anyone else, this book is not bad. I mean, easy, very easy to understand. You can understand the nitrogen laser. It's homemade nitrogen laser, not the commercial kind of, but it can be improved definitely. So you can study more. I mean, if you go to the Amazon, you can buy. It's very cheap kind of book. Okay, so this was the super radiant laser, and these are the you can see on the YouTube. I mean, this is I have shown already. So it's two capacitors are used here, and homemade kind of laser, and when they discharge. So when sorry, something wrong here. Okay. Anyway, this one I have shown already, and let's move to the. This is you can see here. Okay. Okay, so here real cavity optics are starting. Okay, so the cavity optics, what optics are used to build a cavity? There are one thing you have to keep in mind that if you remember, I mentioned that the laser light is polarized. Okay. The sides of the tube or the crystal, they have a certain angles. They should have to avoid losses and to be polarized. So these certain angles are called Brewster angle. Brewster was a scientist. Okay. So Brewster cut. This is Brewster angle. Okay. If you draw a straight line, this angle, whatever it is, it's a Brewster. Okay. With the help of this Brewster angle arrangement, losses are reduced and light become polarized. Okay. And one polarization is almost have zero losses, and other polarization has 100% losses. Okay, so it has only one polarization. There are two configurations here. One possibility, if you have a crystal, to cut like this. Other possibility to cut like this, like here. If we have this kind of angle adjustment here, when the beam will pass from here, it will change its path on returning back. So the beam will misalign. Okay. And if you have this arrangement, in this case, when the beam passes through, it will not misalign. It will follow. It will follow the exact path. Okay. So even if we need to have a Brewster angle, but we also need to think the configuration. So this configuration misalign the system. This configuration keep the system aligned. Okay. So for the cavity mirrors, inside the cavity mirrors, the gain medium, the Brewster angle of the gain medium is very important. Okay. And this Brewster angle, we calculate like this. Theta is equal to tan inverse refractive index of the second medium, refractive index of the first medium. Okay. And if you see in this formula, there is no wavelength. Okay. So angle is entirely depending on the refractive index. Refractive index of the medium 1, refractive index of the medium 2. Okay. So, and but there is some things, if you see this point, the index of refraction may change as a function of wavelength. There are some formulas which I am not showing here, which show the link that with the change of the index of refraction, the wavelength also changes a bit. Okay. But in general, this the cavity, this Brewster cut or Brewster window, and this is this formula is showing it's only depending upon the N1 and N2 refractive index. So the first medium, refractive index, second medium. Okay. So this is the important formula. So whatever material you use, you need to know the refractive index of the crystal or the tube or whatever, medium 1, medium 2. So if this is a crystal here, this is the medium 1 and this is the medium 2. So according to that one, and usually it's, I think it's around 57 degrees, something like this. So you can see in this animation here, you can see in this animation here that this is the incident beam. Okay. And there is no beam coming on this direction, even though angle is twisted here a bit. It's passed through only this one. This one is finished. No beam here. So only this polarization, okay, which can be a vertical, which can be horizontal, polarization will pass through only. This arrangement, this Brewster angle arrangement, because of this Brewster angle arrangement. Okay. I hope you understand this. If you have studied the basic optics in a high school, then you would have known that there are two kinds of mirrors, concave mirrors and convex mirrors. Okay. So converging and diverging, and plane mirrors. So why do you need to know about this? Because in the cavity, you need to use these kind of mirrors. Sometimes you need a plane mirror, sometimes you need a concave mirror, sometimes you need a convex mirrors. So this is a plane mirror here. Simple, to reflect the light. This is a concave mirror and this is a convex mirror. Okay. So in case of a concave mirror, you can see the light is coming here. Okay. And this is the polished surface. Outside is a polished surface. So reflecting surface is inside. Okay. So the light will come back and focus here somewhere, like you can see in this animation. In case of convex mirror, you can see this side is polished and this side is reflecting. So the light comes and is reflected and is diverged in all the directions. So in actual, there will not be any focusing of this light. It's diverging. But if we extend this light virtually, we can find this light is converging at certain point on the back side of the mirror. But actually it's diverging. It's diverge the light in all the directions. So this is your plane mirror here. This is your concave and this is your convex mirror here. Okay. So in case of convex, is strike and it diverge, spread in all the directions. And this is also, you need to know, even though in the cavity, in the normal cavity, we don't use the lens, but in some cavity, we use a lens as well. So type of lens, there are two types of lenses, convex and concave. converge and diverge, converging and diverging. So the convex type lens is converging and concave type is diverging. So the light is coming and it's converged passing through from here and it converge here. Okay. And from here, if the light is coming, it will diverge in all the directions here. But imaginary, virtually, we can see that it can be converged on the back side, okay? Same thing you can see in the animation here. And this is the light is coming and passing through this convex and this is concave. And you can see it's diverging in all the directions here and it's focusing here in case of a convex, okay? So these things which are necessary for you people to know maybe, and this is for your reference, you to study, because you know already that there are center of curvature, there are focal point in case of mirrors especially. It confused you. What is the center of curvature? What is the radius of curvature? And because when you design the cavity, you need to know these values so that you can design a proper cavity of the laser. So radius of curvature, center of curvature, something like this. Okay. So I will finish here now. It's already longer. So cavity optics is not finished, so we'll continue in the next lecture. And I mean, if you have any question, you can ask. Okay. And this slide, last one is don't ask, because this one you have to study by yourself. Okay, so if you have any question, any of you, Gazanfar, do you have?
I have a question in the frequency formula in the previous slides.
Which one?
More back. More back. Okay.
That's the beginning of the slide.
Okay, it's about the 2L is in the
Yes.
bottom
Yes,
and
2L. Yes, it's here. 2L is equal to
the next slide, when you write with hand,
this one.
the next when is the frequency, when you get the frequency in this formula, the next slide.
This one.
Yes, this one. Yeah, if I see in the left, 2 mu by L is above, but in the right is in the top.
This mu. Just a minute. Okay,
Yes,
so
yes, in this one.
this mu.
If I see the right, is the formula is inverted.
Yeah, because here is the lambda and here is the frequency. This formula is same. And if you go to the frequency, here is the frequency. You mean here, this one?
Yeah, yes, in the last formula of the right, on the, when you write with your hand.
Here.
Yes, yes, this.
Just a minute. Probably this I will check it. Maybe this one or this one. There is some mistake. I will correct it. Yeah.
Oh, okay. And in the gain medium losses, gain has to be greater than the losses.
Yeah.
The R1 and R2, there is not one with more reflectivity and other with less reflectivity, or in this case, this don't
No,
import.
in this case, we are studying in general. There are two mirrors. Okay. So the photons are moving to and fro. So we are in general saying that, okay, there are some losses and there are some gain. Okay. So there are gain and there are losses. So this is how. Even in a normal
Okay.
case, even if the mirror is 100% reflecting, there is some absorption as well. So there is losses. Okay. Okay. So
Okay, thank you.
yeah, you're welcome. Okay, Zanfar. Amna Saeed.
Yes, sir.
Hanji, any question? You were sleeping
No,
or?
sir. No, sir.
Keep
Little bit net problem, I think.
Okay.
I didn't hear you.
Yeah, I mean, I don't know, in Pakistan always this kind. Anyway, so the modes you have to keep it in mind. Okay, the ultra-fast lasers and modes are very important. Amna Said, can you hear me?
Yes, sir.
Do you have any question?
Sir, no, sir, I missed some of the cavity optics part due to connection issues. I will cover it from the recording.
Okay. Rusa Hadi?
Sir, also
Yeah, Amna.
L is equals to n lambda by 2 mu. Is mu the refractive index or
Yes,
is it
it's a refractive index. It can be ignored in some cases. It's a refractive index.
Okay, sir.
Rusa Hadi? Tahura Hadi?
Assalamu alaikum, sir.
Walaikum assalam. You have any question?
No, sir, I have no question.
You understand what I'm teaching for last 5-6 lectures?
Yes, sir, but today I didn't attend properly because we have net issue.
But you can
I will.
see the recording.
Yes. Thank you.
So you, both of you sisters are together now, or they are separate? I mean, Tahura is also there?
Yes, we are together.
Tahura, do you have any question? Fatma Noor?
Assalamu alaikum, sir.
Walaikum salam. Yes.
Yes.
Sir, I have no question.
Do you understand why I'm teaching actually?
Yes, sir, but nowadays your lecture are more complicated. And the beginning the lecture was too much easy, but nowadays it is too much difficult for me.
Yeah, but I don't think, I mean, it's too much difficult. Maybe a little bit difficult with the passage of time. But
Yes,
if
sir.
you follow the lectures properly, maybe you can understand. I mean, if you have any question, you can ask. And
Yes, sir.
yeah. And you can also ask the Salman, maybe, if he remembers the course.
Yes, sir.
Yeah.
I try my best. Yes, sir.
But still, it's nothing
you, sir.
actually. The later will come more difficult. So you have to prepare.
Yes, sir.
Even though I'm not teaching the way, I mean, which is the usual way in the universities. But definitely there are some concepts which are takes time to understand.
Yes, sir.
Yeah. Ali Usman.
Assalamu alaikum, sir.
Walaikum salam.
Sir, today's topic is easy and I understand it completely.
Easy?
But,
It was easy?
Sir, because I have already my completed my bachelor and specialized in laser physics
Mhm.
and semiconductor laser devices.
Mhm. Okay. Okay, Ehtisham?
Sir,
Yes,
sir, I have a question.
but you said you don't have a question.
Sir, it's not related to topic, or you can say about it's not a question which is something I didn't understand. It is a bit technical.
Mhm.
I am thinking, what if we double the length of cavity? Like we can get output from a length, and what if we double the length of cavity? Can it amplify the output?
Now, what do you mean double?
Sir, I mean, for example, we can get output from 1 meter length of cavity.
Okay.
And what is,
So use the two cavities.
no, sir, sorry. I mean, if we are getting output from 1 meter length of cavity, then if we increase length to 2 meter of cavity, then what will happen?
First
Can
thing
we
is
get output double,
no.
or
First thing
there
is
will be
that
no output?
no. First thing is that your cavity length has to be according to the wavelength what you want to get. Okay. So
Yes,
if
sir.
if you twice it, then there is a problem that you will not get that output which you are supposed to get. Okay. The cavity length is calculated according to the wavelength. Okay.
Okay, sir. Thank you.
Okay. Ehtisham.
Yes, sir. I have a question, sir. You have mentioned two steady state oscillation conditions, and the second one condition which tells us we can generate a standing wave inside the cavity with controlling the length of the cavity. So in first condition, actually, can we control the phase of the photons that are coming out of the gain media? Do we have a control over it?
No, we may not have a control because whatever the photon is already out of phase, they will be destructive, having destructive interference. And whoever having a 2 pi phase difference, they will be amplifying. So
Yes, sir.
we cannot control this thing 100%.
Okay.
Okay.
Thank you.
With the pump, it's possible somehow, but it's not easy to control this kind of thing. Okay. So it's
Okay, thank you.
much easy to control the length of the cavity. Okay. So, okay, Mauricio, any question?
No.
Okay. Okay. You are the regular person, actually. It's very good to see you in every class. You and David. And there was another one, I think, Mexican guy. He left probably. I don't know. Okay, so Rusa Hadi and Tahura Hadi and Amna Saeed. In the next lecture, they should have a question. Okay? Even you can ask from the previous lectures, okay? Okay, Rusa, Tahura, and Amna.
Yes, sir.
Okay. Okay, then. So thank you very much for attending. And I hope you people to understand the things and to have a better net there so that it's easier for you to understand the lectures. And so if you have any question, you can ask even in the next lecture, okay? So probably, I mean, if you are confused in something or something like this, and you can watch the recording and you can share the recording with your colleagues if you know someone wants to understand or something like this. Okay, so thank you very much, and goodbye, David and Barshu, and Allah Hafiz, all the Pakistanis.
Goodbye, sir.
Thank you very much, sir. Allah Hafiz.
Thank you, sir. Allah Hafiz.
Peace.